Okay, welcome back everybody. So we were discussing in the last class, we had this discussion about Deborah number, and I think quite a few questions came up. So maybe I'll just do a quick recap before we move on to some of the other things. So just a recap. And we had said that there's something called Deborah number where you have lambda by t observation. Right, or the time scale of the observer, and this we had said is some relaxation time scale. Right, and then we had asked what does the relaxation time scale really mean, right? And to understand that, I had posed this particular problem where you have, let's say, two plates, you have some material which is filled in, and I'm not telling you exactly what material is in there, right? So there is some material that is in there, and then we apply a known amount of displacement or strain to this system. And we ask ourselves that to keep this known amount of displacement, so once we apply this displacement and then we have to keep it, what happens to the stress? And we had said if you draw this diagram where this is the time axis and this is, let's say, tau, which is a stress, and here we are measuring the zero of this is after we have applied epsilon naught, and then we are starting to measure what is the stress after we have applied it, and then we want to hold it, right? And then we said that this stress is going to decrease with time for a fluid, and this decrease is going to be characterized by a time scale which will be lambda. So lambda is the time scale associated with this decrease, right? Now, why did this decrease happen? Had this material been a solid, what do you think would have happened? If the material is solid, imagine what it looks like at the molecular or the atomic scale. And if you want to visualize that, one way to visualize is atoms arranged in a lattice structure where they are arranged as if they are connected by springs. All the atoms are, okay. I'm not going to draw the entire network, but that's what I'm trying to do here. Now, once you apply a known amount of strain, all these atoms are getting pulled, right? And they're going to displace from its original location. So they're going to move a little bit further away, maybe. All of these atoms are going to shift a little bit. If the atoms shift and if they're joined by springs, then to keep this epsilon naught, you have to keep that initial amount of stress there, irrespective of the time scale. So in a solid, this decrease of stress would never happen. Instead, you would get a straight line. You would have to keep a constant stress in order to keep this epsilon naught. Right? That's what a solid is. So in a solid body or a perfectly elastic body, there is no mechanism available at the molecular scale for the stress to relax. Because if the stress relaxes, then this epsilon naught goes back to zero. But that's not the purpose. You want to hold epsilon naught at epsilon naught. So in a solid body, that's why we say in an elastic body, I'm holding too many of them, I'll just keep it here. So in an elastic body, energy is stored. because to keep this epsilon naught, you have to keep this amount of stress, and the atoms or the molecules have been displaced from the original position and you're holding them there, right? So this entire, all these springs can be thought of as stretched, being in the stretched form. But what happens if this were a liquid? Well, in liquid you do not have this nice form of particles, right? You don't have this nice arrangement. Instead, you might have a situation where, let's say, all the particles are randomly arranged. So, and when you displace this a little bit, when you displace this box a little bit, all these particles can displace without really changing their relative positions. Or even if at some place, let's say some place you suddenly have a bit of extra packing because of this displacement that you gave, because of thermal motion, all these atoms or molecules are in thermal motion. This can jump out into some other space. So let's say this was a more packed, look, this got trapped in here because you displaced it and you caused at some place particle packing to become higher. This atom can jump out into another available location. So the atoms and the molecules are not in any particular order. They are in a haphazard, they are like a haphazard collection. And since they are in a haphazard collection, you don't have to worry about the order. So the moment once you give epsilon naught, the system displays macroscopically, the system gets displaced, but you do not have any residual stress. The stress quickly decreases to 0. Now there are statistical mechanics ways of estimating what this lambda is for simple fluids, and this lambda can be shown to be of the order of 10 to the power minus 10 seconds or minus 9 seconds for most simple fluids. So the rearrangement is really fast. So for us the Deborah number is 0, right, for the fluids. If you want to understand this even a little bit better, when we were kids, we would play with these things we call kancha. Kancha is basically a glass marble, and we used to have this tons of kanchas in a jar, and then we'd have a game out in the field when we had to hit one kancha with another one. If you keep something like that, glass marbles in a bottle, the kind of haphazard arrangement of the marbles that are there is somewhat representative of the kind of arrangement of matter that is there at the molecular scale for fluids. So since there is no arrangement in the kanchas, you can see that if you change the relative, if you give the jar a little bit shaking, the entire system rearranges, but there is no such relative change, doesn't happen that much. Okay. So how to get to this we won't go into, but if you want to think about it, it's a simple analogy to that would be like the stacking of ping pong balls, a large number of ping pong balls stacked together in a haphazard manner, or the kancha, the glass marbles put in a jar in a haphazard manner. Now, one more thing. So you applied a strain, and then the stress required to hold it to this location has gone down to 0 for a fluid. So you did some work, right, in displacing this, but what is the final state? In the final state, there is no stress in the system. When you began, there was also no stress in the system. So the energies at the end and the beginning are the same. Oh, by the way, one more thing, I hope I had said that in the last class too. This discussion is considering negligible inertia. So this is negligible inertia. Consider inertia to be negligible. Okay. So otherwise you can set the fluid into motion, and then you can have stresses, etc., in the fluid for a much longer period. So we are talking about maybe very thin arrangement. So this is a very small amount of fluid between the two plates and that you are doing this experiment in. So the energy at the beginning and end is the same, but you did put in some work. Where is that gone? Well, that has gone into this rearrangement at the molecular level. It's lost to you. The entirety of the energy that you put in is gone. So in a fluid, so this was solid. So in fluid, energy is lost. All of it is lost, which is why we say the fluid is characterized by viscous dissipation, whereas a solid is characterized by elastic storage of energy. Okay? So this is one more point of difference between the two. Okay, so I think we have had a good recap of that. Okay, so one of the problems that we had given to you was there's a tube and there's fluid in here, and the fluid, it makes an angle of theta. The meniscus makes an angle of theta here. The surface tension was given to you as rho. There's gravity downwards. This was capital D. Fluid density is rho, and the question was, what is delta H, right? And the reason I selected this problem for you guys is because it's a very beautiful example of a problem involving surface forces and volumetric forces, right? So this is a fluid in statics condition. So the net forces, if I have to, so let's say the Z points in the upward direction. So the net forces in Z direction, they have to amount to what? They have to amount to 0. So if I consider this much fluid as my body, then the surface force acting on it is, here you have the surface tension force that will be acting upwards. So this is your sigma into pi d, right? And I hope you have done a little bit of, you have revisited surface tension to arrive at this problem, okay, or trying to solve this problem. So you should do that if you have not. So your surface tension contribution is sigma pi d cosine theta. Okay. And the other component is balanced by gravity, which is doing what? Which is imparting weight to the fluid. So you have rho g into the volume of the fluid. So you have here, okay, so you have sigma d cosine theta minus rho g. And what is the volume? So let us say we neglect this missing volume here, and if we can approximate it, then we will just say that the volume is this much, right? So we can now easily solve for delta H, which will get as This will cancel. 4 sigma cosine theta. There's a pi missing here because I wrote it here. So this pi is gone, right? So you have rho GD. Okay. Good. So that was really straightforward, right? Okay. Now I'm going to erase this. So this was a rather simple problem, and I hope all of you managed to get it. Okay. So just take it down. I'll erase this now. Okay. So we had discussed last time that for fluid statics, our equations, what did they look like? For the 3 directions, where the 3 directions are not necessarily aligned with gravity, you have So I hope you guys are familiar with partial derivatives and all, and all related calculus. We'll revisit some of this in chapter 2 when we look at okay. So now this entire set of equations, this can be summarized. There are 3 different equations that we have. If you want to write it in vector form, you can write it as the negative of something of grad of p plus your rho g equal to 0, where you put a bar over g. So this is my g, which denotes that this g is in vector form. Okay. This particular form we will revisit in chapter 2 what this operator is, but right now it's obvious to you that this operator is basically this set of expressions written in shorthand, but this is a vector equation now. Okay. So these 3 equations, they can be shortened into one vector equation, right? Okay, good. And that is when you have a fluid statics condition. So now let us think about a system. So let's say you have fluid, and this is my z direction and my gravity is acting downwards. Okay. So if you have that and the fluid is at rest, okay, so fluid at rest, then what happens here? Well, these two become trivial, right? So you will have del p del x equal to 0 and del p del y is also equal to 0. These two don't give you much information, so there's no point worrying about these two. So the only equation that you need to worry about is minus dp dz plus rho. Now gz, now just make, you can see here that g is in the negative direction of z. So this is actually minus g here. Okay. So you have this very simple equation. Right? So if I had to integrate, I would have to integrate over these two if I had to solve for them. And let's say I have to solve from some datum z0 to z, where the pressure is known at some p0, and I need to know what p is. If this fluid is incompressible, and if rho is not a function of z, incompressible meaning rho here in the sense that the fluid, the density is not a function of z. If that happens, if rho is constant, if rho is some constant, okay, with respect to z, okay, and the span is not enough for g to vary too much also, then the solution of this becomes very simple, right? You have p minus p naught equal to rho g, and this will reverse z naught minus z. I just took into account the negative sign I have absorbed in here. This equation becomes rather simple to solve if you have a situation like this. But I want to give you a problem to solve for yourself. And we will not be making this assumption. Instead, this material here is, let's say, ideal gas. And if it is ideal gas, then your pressure is given as P is rho times RT, where rho is the density, R is your universal constant, it's a constant here of the gas equation, the ideal gas equation of state. T is the temperature in Kelvin, right? If this were to represent a situation where, let's say, it's air, and we are talking about air as we go up, then for small heights up to a certain region, you have, with increasing elevation, you have a linear decrease of temperature. Okay. So assume that the temperature T decreases from some T naught by some constant times Z. Z being from the datum. Okay. So as height goes up, the temperature decreases. This is valid for a certain range, right? A range of heights. So that is why as we go into the mountains, the temperature decreases, right? It starts feeling cooler, colder and colder. So in this case, your problem, homework problem, this is not exactly a homework problem, it's a self do exercise, and I will not discuss this in today's set of lectures, but I'll rather discuss the solution next week. Okay, so I'll discuss the solution to this particular problem next week. So I'm giving you this problem as something you want to get your hands dirty with. Okay, so once again, pressure for a system where the ideal gas law is valid. So we are talking about a gas and not a liquid. And you assume, moreover, that the temperature linearly decreases with elevation. So the question is, what is my P? Okay, that's your question. Okay, so this is your problem 1. Find P as a function of everything else. Okay, this is self homework in a sense. Okay. I want to give you one more problem to leave you with this, because after this we are going to move on into chapter 2. So you want to have enough problems that you see for the fluid statics case. Okay, so I'm going to erase this part. Okay. So this equation, when we were writing it down, we had said that this is for a fluid statics condition. But what happens if your fluid is not static, but rather the entire fluid is in some kind of rigid body motion with a given acceleration? Okay, so if your fluid is in rigid body motion with a given acceleration, then this side has to account for, okay, this black marker is running out, 1 second. So for a body so if fluid is in rigid body motion with acceleration vector A. Okay. So I've just broken this down into AX, AY and AZ. Okay. So if you want to combine this, all you need to do is to write this entire thing as minus gradient of pressure plus rho G equal to rho A vector. And here I want to give you one more sample problem to solve, which will, get you to work this out, and that will be, so sample problem. And this sample problem involves a cylinder, and you can take this as D, so the radius is R, and it was filled with fluid in the beginning. So let's say this was fluid, and this height initially was h naught, and then what you did is you put this entire system, you started rotating it about its center of its axis, which goes right to the middle of the cylinder. And if it starts rotating at an angular velocity of omega, then what is going to happen to this? It's going to distort. This fluid profile is going to distort. So question is, this height will change here, so it will no longer remain h naught. This height will change to some other value, let's say h1. Okay, I hope you can see this. This should be large enough. So can you find out what this new shape is and what this value of h1 is? When you are doing this, do not worry about the issue of surface tension like we did last time. That was a separate case. Okay, so here you can assume that the tube diameter is large enough so that this entire profile initially was flat and had a height of h naught. So this distortion here is only due to this imposed omega, and you are being asked to find the relationship of this profile or h1 with omega, and we are telling you that this entire system is working as if the fluid is in rigid body motion and not as if the fluid is moving. If the fluid were moving, then this solution would be far more complicated. So you are just looking at a case of it's almost as if the entire fluid is in a static condition under quotes, but it is behaving as a rigid body with a certain acceleration, but it's not moving inside. So there's no churning happening. If the fluid starts flowing inside, then the problem becomes much more complicated than this. Okay. So I will leave you with this particular problem, and I'm not going to. So next part of the lecture, I'm going to start on chapter 2, and we will revisit this problem in the next week's lecture. Okay, fine. I have given you 2 problems this week to try your hands on, and both involving fluid statics, right? Okay, good. Okay, so we will stop our class here.